everyone, I'm Taz Singh, and this is a picture of me from a prior summit, back when I was younger but still quite foolish. Since that summit, I've gained a bit of a reputation for being able to take perceivably insurmountable challenges and breaking them down to be understandable enough for an elegant solution to be applied. Today I'm here to tell you about one of such stories, which has been my team's area of focus for the past 2 years. You see, we've been contracted by a large publicly traded corporation to assist with their data architecture. And well, this is actually the very first engineering presentation that corporation's ever given. So without further ado, I'd like to tell you more about our story at Residio. Don't recognize that name? Well, maybe you've seen this slide at Apple's WWDC keynote last year. And over here, you'll see that Residio name once again, alongside other industry members such as Google, Amazon, Apple of course, IKEA, SmartThings, and so on. You've likely clued in by now that it's an Internet of Things company, but why is the name so foreign, especially given the companies keeping on the slide? Well, what if I told you it's actually a Fortune 100 company in disguise? That's right, it's really Honeywell in disguise, because you see, back in 2019, Honeywell spun off its home division to form Residio. And with that spin-off resulted in Residio taking on the large data heritage that Honeywell had, including, well, now taking over the Honeywell Home app itself. It's now called Honeywell Home by Residio. Along with that app came a few more, including all of these that we can see from the Apple App Store. Of course, these are just the Apple apps. It doesn't include all of the web apps and Android apps that Residio also took over. But anyway, just to name a few on this screen, we have Total Connect Comfort, that Honeywell Home app I mentioned before, Total Connect 2.0, WBox, and I don't even know what that is, AlarmNet 360, and so on. And the thing about each of these apps is that they all have different user account systems because they have different backends entirely as well, with very few of those components shared amongst each other. So because they have different user account systems, if you have a user account on one, that doesn't mean that you'll be able to log in with that same user account on another. They're basically incredibly fragmented systems. And on top of that, they're all at immense load. I'm actually told that one of these backend systems has an ingress volume of around 13 billion requests per day. By comparison, I'm told that Twitter only has an ingress volume of 9 billion requests per day. Each of these even has their own business, their own product, their own development, their own design, and their own marketing teams. They basically operate as independent companies under a Residio umbrella. Now, on top of that, Residio has made a few acquisitions. Of course, all of these systems are entirely different to Residio's because they're built by entirely different teams. Of course, they have different user account systems. Of course, they have entirely different backends because they're acquisitions. Now, how would we even go about integrating these acquisitions into even just the first row of Apple apps I mentioned before? Each of those have different user accounts. Each of those have different backend systems. What's the effort to effectively integrate any of those? Does it look something like this? Is it a custom integration for each app, for each acquisition? That's a bit crazy. And furthermore, what happens when Residio acquires yet another company like this one that I found out about while researching this talk? Does that become a set of custom integrations all over again? How do we effectively scale and maintain this with a limited group of engineers? Fundamentally, how do we go about acquiring a data graph? Well, this was the exact problem that my team was contracted to solve, because what we truly want is to get rid of all this garbage. And instead, what we want one single data graph for all of Residio. We want all of the data providers to report into that consolidated data graph, and we want the data consumers to be able to operate on top of it. Okay, so we have a general action plan moving forward, but where do we even start with this? Well, given it's a GraphQL talk, let's go ahead by applying some graph thinking. Typically, when looking at new data systems, I like to think about how I relate to the data system. So let's start with me, and one node which represents me. So how do I relate to the Residio ecosystem? Well, inside Residio, I would have a house, and that house would have a bunch of smart devices inside of it. But of course, this isn't quite how we model things inside GraphQL. We wouldn't model things quite literally by the things that are represented in the world. We'd instead group these entities by the types that they represent. So instead, I would become a user, the house would become a location, and the devices, well, they would just be devices, of course. So we can simplify that object graph into an entity graph by just saying a user has a location that has devices. Okay, so I have a pretty simplistic model of how I could relate to a device within the Residio ecosystem. Now let's check if that hypothesis actually holds true across the systems that we're evaluating. So Thankfully, a user that has many locations, that has many devices, does seem to hold true in quite a few of the Residio systems. However, when we start evaluating more systems, there's an account that has a home that has the same definition of device that we had in the first system. And if we were to look at another system, it's a customer that has a service account that has a security alarm panel. And actually, while evaluating that third system, we found out that the first system doesn't hold all types of devices, it only holds thermostats, in fact. Okay, well, this level of fragmentation makes it incredibly difficult to answer very basic questions, such as how many users do we have? How many devices does a user have? All of these types of questions are incredibly difficult because no system can even agree on what a user is. The systems don't even call a user in the first place. They don't even agree on what a device is because they don't even have a common definition of what a device is. So going back to my original question, does the hypothesis hold? It doesn't seem like it does. It seems like the systems are way too fragmented for that hypothesis to hold true. So where do we start our data unification effort, given this fragmented data landscape? Well, first things first, we should align on naming. It doesn't help that every system calls everything by different names. Let's first start by applying the same name everywhere. So we started out with this entity graph. Let's just start by calling everything that could be a user, everything that could be a location, and everything that could be a device. Now, of course, it's a bit more complicated than this in reality than just changing the names, but you kind of get where I'm going. We have to align on the naming, first of all, across teams and across systems in order to start to try to chip away at the problem. So at the very least now, we're all talking in the same terms. So instead of this being a representation of terms, it's now a better representation of which entities are held within each system. And so how do we go about describing these systems now? Well, thankfully, around the same time we were exploring this problem was around the same time that Apollo Federation started picking up in popularity. And through that same time, I happened to learn quite a bit more about Apollo Federation. And one of the things that I really like about Apollo Federation is a principled GraphQL site that was marketed alongside it. You see, it very directly aligns with what we want. We want one data graph which catalogs the entire data offering. We want it to represent the different systems in a federated implementation. We want to track schemas in a registry as a single source of truth of what should be within that one data graph. And I'll talk a little bit more about those agility principles in the later part of this talk, but so far, it aligns pretty well with exactly what we want. Yeah. But let's talk a little bit more about the technology itself and things that I like about that. Specifically, Apollo Federation defines a common protocol for federated graphs to combine into one data offering. It comes with a query planner that looks at the various data graph definitions and determines how to execute any GraphQL operation across that federated cluster. This is a little bit different than other GraphQL schema merging tools where you may have to define your own protocol, but of course, as with all things, they all have their trade-offs at the end of the day. Okay, so taking the entity graph that we've been working on, let's assign a few labels to them, A, B, and C, so system A, system B, and system C, and let's actually start writing it out in GraphQL. So I could define a system A user as such, and I could define a system B user as such, and I can add both of those to the top-level query entry point of our data graph. So now if we were to execute a query against that data graph, a query could look like this, where we want a first name from system A, we want a first name from system B. And if we were to execute that operation, we could get a response that looks like this, where system A responds with the first name. We could also get a response that looks like this, where system B responds with the first name. Or we could get a response that looks like this, where no system responds with anything. Perhaps we aren't authenticated yet to try to get that type of data. And fundamentally, in every single case, it's up to the data consumer to implement logic to reconcile all of the different permutations of data that the schema technically allows. Because what would happen to a data consumer if they got something like this, where both systems respond? Thankfully, the data in this case are equivalent, but what if they're different? Does the data consumer now need to start writing precedence logic to determine which system it prefers the data from? What happens if we were to introduce system C into the mix? Would we then have to update every single query for every single data consumer to start considering system C, and then determine precedence logic on top of that for all of the new permutations for responses that are possible now? Well, this is a valid approach when it comes to data unification, and we actually call this approach branching. Branching is when we expose the data literally through different data graph branches in order to better rationalize the data dimensions at play. Fundamentally, this allows us to see the data, which allows us to better understand how it's interacted with, fundamentally leading towards more optimal data unification strategies in the future. This is a learning step. This gets us to a point where we can rationalize the data much more effectively. Okay, so branching enables us to model this entity graph very literally with all of the trade-offs that come with that. But what if we can do better? What if we can model the entity graph in a manner that's as simple as this, but is still extended with the unique attributes that are present within each system? Thankfully, this is where GraphQL data expressivity really shines. GraphQL's sophisticated type system enables us to express a variety of data architectures in a manner that's simple for data consumers. Okay, so let's take the GraphQL schema that we had before, and let's go ahead and introduce an interface to the mix. Now we can compose that interface onto the types that we had before, and we can update the top-level query entry point to simply have a field called viewer that resolves to that interface. Now we can go ahead and update our query. So instead of having a list of every single system in a query, we can just say, get me the viewer's first name. Immediately, you can see how much cleaner and how much more predictable this operation becomes for data consumers, while still enabling data producers to express themselves with a level of sophistication. So now the response to that operation can simply be the first name of Taz, or it can be null. It's that easy, and that's it. It's dramatically more predictable for the data consumer to reason about the permutations of data that they're getting. And if we did happen to care about which system is responding with data, we can simply ask for a type name, and we can ask for more information only present on a particular type. In this case, system B user has a name prefix that we could be interested in, so we can grab that as well. We could get a response like this if system B was a source of truth for this data. So we call this approach core entity normalization, where we leverage GraphQL interfaces to expose common data fields as if they were being provided by a singular source. This approach is best for data consumers, but may require us to gap fill pieces of the schema that differ between interface implementers. For example, we need to provide a resolve type at the very least in order for our federated implementation to figure out which system to pull data from. And of course, we can only get to this stage once we have an understanding of what commonalities are within the data architecture, which we can only achieve through the branching approach from before. Okay, well, this is all pretty cool, right? We've gone through a few different strategies of data unification. Like now we can hopefully just build it, right? That's as easy as that, right? Well, not really. All we've really done so far is talk about the general shape of what we want to build. Actually building a fully executable federated cluster of services is a whole different story, and there's a whole lot of other data dimensions at play. So far, we've only really talked about schema shape, which is provided by the GraphQL schema definition language, and we've talked about federated schema ownership, which is supplied by Apollo Federation. But what about entity relationships, which are the bidirectional associations, in our case, between a user, their locations, and their devices? What about referential integrity? If I refer to a given user, I want it to be that exact same user referenced throughout the myriad of ways that I can access that user throughout the data graph. Data pertinence. My name is Taz. It's not some random characters that formulate a string, it is Taz. Data mutation. What are the rules around how I can change the data? How am I allowed to operate on every field? Are certain fields required? Data authorization. What governs the data interactions that I'm allowed to perform? And last but certainly not least, data persistence. Even then, this is not an exhaustive or academic list. This is just whatever I thought of. I'm sure there are other data dimensions at play that I haven't explicitly mentioned here. But if we were to wait for teams to determine and build all of these different various data dimensions into their federated services, we would probably be waiting for a long time before data consumers were actually given anything usable. And even when they were given something usable, if they didn't like it, what happens then? The data producer has to go back and redo their database tables, migrate their data, rebuild another executable schema for yet another round of evaluation. This is where we fundamentally needed a solution to continually deliver business value while working through the myriad of data realities that exist at large companies with the sort of data heritage that Residio has. So what our team came up with was very unique for our problem space. That is GraphQL simulation. This enables data-consuming teams to rapidly iterate on product requirements, while data-producing teams concurrently turn that schema contract into reality. We ended up calling our solution GiraffeQL, and I'd like to demo it publicly for the very first time just for you. Awesome, so let's take a look at GiraffeQL. I don't have enough time to go over the schema in a lot of depth, but I'll touch on critical high-level points that I wanna highlight for you. First things first, you'll probably notice that this is not using a schema-first style of GraphQL definition. This is using a code-first style. And the reason we do that is because it allows us to co-locate the definition of all those different data dimensions on the same type. We also follow a relay schema specification, which means that we have interfaces such as node and so on and so forth. But anyway, moving forward, we can see this is the same core user interface that we had defined before. We have that first name field, we have that last name field, we have data pertinence. So basically what this will say is that for the first name field, we want it to look like a first name. It's pertinent to that field definition itself. I've also gone ahead and defined locations on this demo. So here we can see we have a paginated list of locations. It is a core location interface type. And critically, the inverse of this location relation is the owner relation on the location itself. So basically, for a given user, they have a list of locations, and from a locations perspective, it's the owner that relates back to the same core user. So if we were to look at the definition of a core location interface, we can see that an owner here has an inverse of locations as the relation that relates it back to the list of locations for a user. I hope that makes sense, and I hope it makes a bit more sense if we start executing queries. So we have a viewer. We want to grab the first name, last name, and ID. We can see we got some data here. We got a Clemmy Kremen this time. And down here we can see the federated query plan to let you know that it is executing a fully functional federated simulated cluster. And in fact, we have a system B definition over here. Again, I won't go into this in a lot of detail, but simply know that it does physically exist. But okay, let's take a look at this ID over here. And let's execute that on a node query at the top level here on core user. Let's grab the ID again. Let's grab the first name and last name. So we can see that we get Clemmy Kremen again. So we have some sort of level of referential integrity across these two tabs. We're getting the same type of data for the same user again. But okay, I think we can do better than that. Let's go ahead and grab a location. Let's grab the first location, and let's grab the edges, node, ID, and name of that location. So this is Clemmy's second home, and by grabbing that ID there, let's pull it up inside node over here on core location. Grab the ID again, grab the name again, and we should hopefully get the second home. Bam, there it is. But we can go even further than that. Let's take a look at this field definition here and how we can relate back to a list of locations. Let's grab the owner and let's grab their ID and first name, last name once again. And there we can see that the owner of this location is Clemmy Kremen, the same Clemmy Kremen as in the first example. That's a funny name. Funny for faker. Anyway, I hope I've demonstrated that with a very declarative style of defining schemas, we can co-locate all of the data dimensions through simulation to make sure that we've provided data consumers with a path forward on iterating on their product requirements, while concurrently a data producer can go ahead and fulfill the schema contract. Perfect. I hope you enjoyed that. Well, let's talk a little bit about the future of GraphQL at Resideo. We want to continue working on real-time GraphQL. The nature of the data at Resideo is inherently real-time. Your thermostat could report different temperature measurements, and you want to get all of that in real time. We want to work on server-on-client GraphQL. So GraphQL, in my opinion, is a technology that best describes data dependencies that are external to the system that you're currently operating on. For example, if you're a mobile app developer interacting with a device over Bluetooth, that device's data is external to their mobile app that you're working on. What if we were to extend the GraphQL schema on that mobile device to apply a schema to the actual data from your thermostat, thus making it easy for mobile developers to pull in any sort of data expressed through GraphQL without caring about where that data physically lives? I want to work on GraphQL for embedded systems. Of course, being an IoT company, we have plenty of embedded systems that could benefit from graph technology. I mentioned before that we have that large ingress point, about 13 billion requests per day. What if that reported directly into GraphQL and reported directly into our federated data graph? What benefits could we see there? And fundamentally, if you're interested in working on any of these challenges, Residio is hiring. Please check out the careers page for more info, and I'm actually told that there'll be a GraphQL specific role being added on there shortly. If you follow me on Twitter, I'm more than happy to tweet out a link directly to that role whenever it's added. But if you enjoyed this talk, it wouldn't be here without my team. So thank you so much to everyone that worked on this. Thank you, Brian. Thank you, Imran, Jordan, Marcel, and Shane. These are their Twitter or GitHubs if you want to follow them more. And thank you to everyone else that I haven't had a moment to explicitly thank in this talk. But fundamentally, thank you so much for listening. I hope you enjoyed it. Bye for now.